Welcome to Lesson 4 of Module 3, where we will covering ResNet and the trade-offs of depth and model performance. We'll discuss the trade-offs of depth and residuals, ResNet, and batch normalization. Let's begin by considering the trade-offs of depth and residuals. The story of deep learning is one of learning a hierarchy of layers, each of which represents increasingly abstract features of data. Deeper models should always perform better, at least in terms of training accuracy. However, it can make the training process more time-consuming. The model might also be more susceptible to overfitting, and it can also make the network more sensitive to small changes in the input data. One issue with deep models could be the vanishing gradient problem, which can occur when you train deep neural networks with many layers. Introducing a new method using residual layers improves model performance. Residual layers tend to maintain accuracy better than dense layers in a deep network. This is because residual layers allow the network to learn more complex functions, while dense layers tend to overfit and might become less effective as the network becomes deeper. By using residual connections, data can skip layers and reach later parts of the network. The plus operation is a simple element-wise addition of x to the transformed output f of x from the network layer. Residual layers result in easier convergence in neural networks and mitigate the issue of vanishing and exploding gradients. The exact reason why residual connections work is still being researched, but some theories support the results. The reasons are covered in the following slides. The slide shows an example of a regular block and an example of a residual block. In the regular block, the portion within the dotted line box must directly learn the mapping f of x. In the residual block, the portion within the dotted line box needs to learn the residual mapping g of x equals f of x minus x, which makes the identity mapping f of x equals x easier to learn. Consider uppercase F, which is the class of functions that a specific network architecture, together with learning rates and other hyperparameter settings, can reach. That is, for all lowercase f in uppercase F, there exists some set of parameters, such as weights and biases, that can be obtained through training on a suitable dataset. Assume that the desired underlying mapping that you want to obtain by learning is lowercase f star. Adding layers doesn't guarantee that the next function class is a superset of the function class that is represented by the previous layer. In other words, it's possible for the function class to move away from the initial function class as is represented by prior layers. This shift can restrict the expressiveness of the network and cause instability. Thus, only if larger function classes contain the smaller ones is it guaranteed that increasing them will strictly increase the expressive power of the network. For deep neural networks, if training the newly added layer into an identity function, fx equals x, the new model will be as effective as the original model. Because the new model might get a better solution to fit the training dataset, the added layer might make it easier to reduce training errors. Residual connections provide the skip layer with the inputs provided to the layer before. This allows the skip layer to represent a larger function class, which includes the class of functions that is represented by the previous layer. By adding a layer, you risk losing the benefits from the original layers in the training process. Adding an extra layer doesn't guarantee that performance will improve. This happens because, in the function space, the new class of functions that represent the new architecture is not fully contained in the original function space. If you add a skip connection, the larger function classes contain the smaller ones. This guarantees that increasing the number of layers strictly increases the expressive power of the network. For deep neural networks, if you train the newly added layer into an identity function, fx equals x, the new model will be as effective as the original model. Because the new model might get a better solution to fit the training dataset, the added layer might make it easier to reduce training errors. The figure on the left side represents the region that spans all the functions that are represented by a generic network architecture. As k, the number of layers, increases, the resulting region shifts further away from the optimal point. This is because, as k increases, the new region doesn't contain all the functions that are represented by the previous network. Therefore, the deepest network often fails to be the better solution. The figure on the right side represents a network that uses skip or residual connections. When a layer is added, all the functions of the previous network architecture are contained in the new region. Therefore, increasing the number of layers results in a better performing model. For non-nested function classes, a function class that is larger, by area, doesn't guarantee that the function will get closer to the truth function, f***. This doesn't happen in nested function classes. For deep neural networks, if you train the newly added layer into an identity function, fx equals x, the new model will be as effective as the original model. Because the new model might get a better solution to fit the training dataset, the added layer might make it easier to reduce training errors. This is the question that he et al. 2016 considered when working on deep computer vision (CV) models. At the heart of their proposed residual network, ResNet, is the idea that every additional layer should more easily contain the identity function as one of its elements. These considerations are rather profound, but they led to a surprisingly simple solution, a residual block. With it, ResNet won the ImageNet Large-Scale Visual Recognition Challenge in 2015. The design had a profound influence on how to build deep neural networks. In the case of residual layers, the gradient can flow directly from the output of the layer to the input of the layer, bypassing the intermediate layers. This can improve the flow of gradients and prevent the vanishing gradient problem. The gradient will still hit each layer separately, as well as in all combinations. This is because the gradient is computed for each layer individually, using the chain rule to propagate the gradient backward through the network. The gradient will still hit each layer separately, as well as in all combinations. This is because the gradient is computed for each layer individually, using the chain rule to propagate the gradient backward through the network. The use of residual connections doesn't change this basic principle of backpropagation. In deep networks with many residual layers, the gradient might hit each layer multiple times through different paths, depending on the specific architecture of the network. This can be beneficial for training deep networks because it allows the gradient to flow more freely and reduces the risk of the vanishing gradient problem. The theory of residual layers and their benefits is quite extensive. Here are some resources if you'd like to learn more. Ways that residual connections can help regularize a neural network and prevent overfitting, but they might also introduce noise into the network. Reduce the vanishing gradient problem and improve the flow of information through a deep neural network, but they might also increase the memory requirements and computational complexity of the network. Improve the robustness of a neural network to variations in the input data, but they might also introduce new sources of error or instability. Simplify the training process and reduce the number of iterations required to achieve convergence, but they might also increase the risk of overfitting. Improve the interpretability and explainability of a neural network, but they might also make it more difficult to analyze and interpret the internal workings of the network. Deep neural networks with dense linear layers aren't always as effectively trained as shallower models because the family of functions they represent is not nested. This limitation can be addressed by adding residual connections, which allow a final layer to be bypassed with skip connections. These skip connections improve the gradient flow through the network, as layers can be bypassed during the backpropagation process. By nesting the family of functions represented by the network, residual connections facilitate more effective training of deep neural architectures compared to traditional dense layers alone. Let's continue with ResNet. Degradation occurs when the network depth increases and loss rebounds. How can this be addressed? There is a deep residual learning framework called ResNet. In a traditional neural network, each layer applies a nonlinear transformation to the output of the previous layer. In contrast, a residual block in a ResNet contains a shortcut connection that bypasses one or more layers and adds the input directly to the output. This allows the network to learn the residual function, or the difference between the output and input, instead of trying to learn the full function from scratch. The introduction of residual connections allows for the design of much deeper neural networks that can be trained more easily and effectively. With traditional networks, adding more layers can sometimes lead to worse performance due to the vanishing gradient problem, where the gradients become extremely small and the network stops learning. ResNet overcomes this issue by allowing gradients to flow directly through the shortcut connections, which helps to preserve the gradient magnitude and enables training of much deeper networks. Residual skip connections, also known as residual connections, are a type of shortcut connection in deep neural networks. These connections allow the network to learn residual functions, which can help to improve the quality of learned features. In a traditional neural network, the output of one layer is directly fed into the next layer as input. However, in a residual network, the output of a layer is added to the input of a later layer, effectively creating a shortcut connection that allows the network to bypass some of the layers. This connection is often called a skip connection. The intuition behind this approach is that when a neural network learns to approximate a complex function, it might be easier to learn the residual function, the difference between the output and the input, rather than directly learning the underlying function itself. By using skip connections, the network can learn to adjust the input features for higher quality features, which can improve the overall performance of the network. The basic idea behind residual blocks is to add the input x to the output f of x of the block. This simple concept has two crucial implications. Firstly, it allows the model to effectively ignore a particular block during training by learning f of x equals 0, ensuring that the overall network's function class encompasses the function classes of its smaller subnetworks. Secondly, in practice, learning the deviation from the identity mapping is simpler than learning the entire function from scratch. This is because it is easier for the network to learn the residual mapping that refines the input features, rather than having to learn the complete transformation directly. By facilitating the learning of residual mappings, residual blocks provide an efficient way for the network to progressively refine and enhance the input representations as they propagate through the layers. In summary, ResNet varies its depth by repeating residual blocks of the same structure. The number in the ResNet name, such as ResNet 18, ResNet 34, ResNet 50, ResNet 101, or ResNet 152, indicates the number of convolutional layers in the network. For example, ResNet 18 has 18 convolutional layers. Generally, deeper models can achieve higher accuracy, but at the cost of increased computational complexity. The ResNet architecture employs two pooling layers for dimensionality reduction, which helps to downsample the feature maps and reduce the spatial dimensions. Batch normalization is also used for capacity control, which helps to stabilize the training process and improve the model's performance. Let's now discuss batch normalization. Why do we need batch normalization in deep neural networks? Firstly, internal covariate shift refers to the issue where the distribution of input activations to each layer can shift during training, leading to slow convergence and instability. Batch normalization helps mitigate this by normalizing the inputs to each layer. Secondly, deep neural networks with many layers can suffer from vanishing or exploding gradients during training, which can prevent the network from learning effectively. Batch normalization helps to stabilize the gradients and enable more stable and efficient training. Finally, overfitting is a common problem where the neural network becomes too specialized to the training data and fails to generalize well to new, unseen data. Batch normalization acts as a form of regularization, reducing the reliance on other techniques like dropout, and improving the network's ability to generalize to new data and perform well on test sets. Batch normalization offers several benefits for training deep neural networks. It helps address the internal covariate shift issue by normalizing the input activations to each layer, ensuring they have zero mean and unit variance. This leads to faster convergence during training. Additionally, batch normalization can mitigate the vanishing and exploding gradients problem by preventing the gradients from becoming too small or too large during backpropagation. The normalization process also adds noise to the input activations of each layer, which acts as a form of regularization. This helps reduce the network sensitivity to small changes in the input, improving its ability to generalize and reducing overfitting. Furthermore, batch normalization can improve the flow of gradients through the network during backpropagation, enhancing the stability of the training process. Batch normalization is a technique that is used in deep learning to improve the training. The technique normalizes the output of each layer so that it has zero mean and unit variance. This makes it easier for the network to learn and leads to faster, more stable training. Normalization is done by computing the mean and variance of the inputs over a batch of training examples, and then normalizing the inputs by using these statistics. Batch normalization also includes two learnable parameters, scale and shift, which allow the network to learn the optimal scaling and shifting of the normalized inputs. Normalization is applied by subtracting the sample mean and dividing by the sample standard deviation. In the example on the slide, the sample is one batch. Scale and shift parameters are learned through the training process. These parameters allow the network to adjust the scale and mean of the normalization. After applying standardization, the resulting minibatch has zero mean and unit variance. The choice of unit variance, compared to some other magic number, is an arbitrary choice. The degree of freedom can be recovered by including the element-wise scale parameter gamma and shift parameter beta. Both are parameters that need to be learned as part of model training. Batch normalization typically behaves differently in training mode and prediction mode. First, the noise in the sample mean and the sample variance that arises from estimating each on minibatches isn't desirable after the model is trained. Second, you might not have the luxury of computing per batch normalization statistics. For example, you might apply the model to make one prediction at a time. Typically, after training, you will use the entire dataset to compute stable estimates of the variable statistics and then fix them at prediction time. Consequently, batch normalization behaves differently during training and at test time. Recall that dropout also exhibits this characteristic. The code that is provided on the slide presents a function that implements batch normalization from scratch. The residual class in this code snippet shows two fully connected layers, self.dense1 and self.dense2, with rectified linear unit, ReLU, activation functions, and adds the input tensor x to the output tensor of the residual layer. The forward method takes a tensor as input and returns the output of the residual layer. In this example, the residual block has two 3x3 convolutional layers with the same number of output channels. Each convolutional layer is followed by a batch normalization layer and a ReLU activation function. Then, the two convolution operations are skipped, and the input is added directly before the final ReLU activation function. This kind of design requires that the output of the two convolutional layers is the same shape as the input so that they can be added together. If changing the number of channels is needed, introduce an additional 1x1 convolutional layer to transform the input into the desired shape for the addition operation. There are pros and cons of batch normalization, a technique used in deep neural networks. Batch normalization improves training speed by allowing higher learning rates and reducing the need for careful initialization. It also enhances generalization by reducing overfitting and helps to mitigate the vanishing and exploding gradients problem. However, batch normalization increases memory usage as it requires storing the mean and variance for each batch during training. Its effectiveness also depends on the batch size, and it can slow down inference time due to the additional computations required for normalization. When training deep neural networks, it is essential to weight the trade-offs between the benefits of faster convergence and better generalization against the potential drawbacks of increased memory usage and slower inference. Batch normalization has proven to be an effective technique in many applications, but its impact may vary depending on the specific architecture and dataset. Careful consideration of these pros and cons can help optimize the training process and achieve the desired performance. In the next lesson, you will learn about modern architectures. Thank you for watching.